Just before I bring Will Sikkema out here, he of the magic glue that is necessary to reconnect severed heads and spinal cords. We're talking about a 36-hour procedure that's going to involve around 150 people. It's estimated to cost $12 or $13 million. And it is proposed not by a crackpot, but by a crack surgeon, a famous Italian surgeon called Sergio Canavero. And he is looking for an appropriate venue, and he is looking for an appropriate sponsor. But his modest proposal is that he will sever a head and connect it to another body. He has a volunteer, a fellow called Valery Spiridonov, who is suffering from a wasting disease. I feel I may be stepping on some of your talk, William, so come on in. But the point is, none of this would be possible without this magic thing that William Sikkema, a Canadian graduate student, has invented.
So I'm William Sikkema. I'm a fourth-year PhD candidate at Rice University, but I'm originally from Vancouver, British Columbia. So it's good to be home. So I'm going to be talking about head transplants and graphene nanoribbons, but I'm a chemist, and what has a chemist got to do with a head transplant? Like that's surgeons and biologists, right? Well, in my experience, new ideas generally come from hard problems and a multidisciplinary approach. So you take people from various different disciplines. So you take chemists, physicists, biologists, doctors, surgeons, and you put them in a room and you give them a hard problem. And we've seen hard problems before today. So this hard problem is the head transplant. So if you have a person who has a healthy head, but they have a damaged body, say they have some sort of cancer that's throughout their body but has left their head alone, or they have muscular dystrophy like Valery, you mentioned, where their muscle is sort of wasting away and they're essentially skin and bone, but their head is mostly intact. Or some person who has had severe trauma where their body is unrecoverable. You could take their healthy head and transfer it onto a healthy body of a person who is either brain dead. Or you could take some vegetables and cellularize them to make a body and transplant the head onto the healthy body. But that's probably a little bit farther away. So then we're going to cue the video to watch how the procedure would work from Sergio's perspective. And here it is. So what's the hardest part of a head transplant? Is it the arteries and veins? Can we reconnect those? Well, we do, yes, we do heart transplants and kidney transplants and I guess lung transplants fairly routinely. Can we reconnect muscle and bone? We do hand transplants and arm transplants less routinely, but that's still possible. So what's left in the neck? It's the nerves, so the spinal cord. Can we connect nerves? And peripheral nerves, which are the nerves that control your muscles and the extremities of your body, and those are the nerves that receive signals back from your senses, those nerves can regenerate, but not the central nervous system. The central nervous system is your brain and your spinal cord and your optic nerve to some extent. So those can't be regenerated, and I'll talk a little bit about why. So the hardest part of the problem is Sergio's paper that he published here. He had a solution. He had a solution for fusing the spinal cord, And I was aware of this about a year and a half ago, and then I emailed him saying, I potentially have a nano solution, a solution that's more multidisciplinary, that could potentially do a better job at repairing a spinal cord. And he said, sure, let's try something. So then I gave him some material, and you'll see the story as it progresses. We need to understand various different parts of the magic glue, the graphene nanoribbons that repair the spinal cord. So I'm sort of going to pull the curtain away from the magic, and so you can see the details of what's going on. So we need to understand three things. First, how we build nanomaterials, which requires chemistry, how neurons grow after damage, which requires biology and medicine, and how nanomaterials interact with biology, which requires chemistry and biology. So this is a lot of different people, a lot of different expertise, all coming together to solve one really hard problem. So the first one is how to build nanomaterials, and this is mostly chemistry. This is the part I'm really excited about, because I'm a chemist. So we start with this thing called graphene nanoribbons, so they're carbon nanotubes. So carbon comes in various different forms. A lot of the girls have diamonds on their hands. That's the form of carbon. Also, pencil lead is a form of carbon as well. But this is a very special form of carbon, where the carbon is all connected in a hexagonal lattice, and then it's sort of rolled up into a tube like a straw. And you can sort of see the straw going like that. And then to make these into graphene nanoribbons, what you do is you sort of inflate them and you break them. So the same way a pipe would freeze in winter, if there's water in it, the water expands, the pipe sort of breaks longitudinally along that way. So it sort of unfolds and you get this long, thin nanoribbon structure. But these are not water soluble, so they don't interact well with biology. It's sort of like taking a pencil and putting it into a human, and it's not going to interact well. If you've accidentally stabbed yourself with a pencil, you see that black mark, it stays around for a very long time. So like oil and water don't mix. So you have to make these water interactable to some extent. So this is how chemists describe things. So this is the hexagonal lattice, and every black sphere is a carbon atom, and every red sphere is an oxygen atom. And because there's not a lot of oxygen here, it's not very water soluble, and so we need to add oxygen atoms to it. So we're going to take this molecule here and add it to this molecule to show how it happens. But it doesn't make a lot of sense. Like how does this molecule go to this molecule? So now I'm going to show you how chemists see these molecules. So all the red spheres are negatively charged, and all the green spheres are positively charged. This is sort of an approximation, but it'll give you the general picture. So because there's positive charges here and negative charges here, there's some sort of attraction that happens between the two of them. And they come together, and as they come together, then they will form a bond. So that's a new connection. So now these carbon atoms are connected, and this carbon atom is no longer connected to that one. So then it can swing open, and now you have a new negative charge at the end of it, and then another one can come in and reconnect. And now you're adding lots of different oxygen atoms, so now the whole overall structure is becoming water soluble. So that'll connect and again and again and again, and that'll not only happen to this carbon atom, but all these carbon atoms along the thing. So the whole structure becomes water soluble, so you can put it inside a biological system. So you see that connecting there, and then this is what it would overall look like. And this is how chemists describe the process. So it's a little bit harder to understand, but you have this multi-wall carbon nanotube, and you get a stack of graphene nanoribbons. When you sort of inflate it with metals, you use sodium and potassium to react inside, and then you get this structure here. And what do they look like? So this is scanning electron microscopy and transmission electron microscopy. So instead of using photons to look at these things, we use electrons to look at these things, so you can look a lot smaller. And this scale bar is 10 microns. The smallest human hair has a diameter of about 100 microns. So this is about a tenth of the diameter of human hair. And so you can see that they're actually fairly long as far as molecules go. So you can see this molecule on that kind of scale. And then the width, this is a 10 nanometers. So that's 1,000 times smaller than this. So now you could stack 10,000 of these side by side along a human hair. So they're very long and very thin. And that's really important for how neurons grow. So we'll see that in a second. So how do neurons grow after damage? That's the second part of the puzzle we need to understand. I'm pressing the button. There we go. So this is an image of what a neuron looks like when it's growing. So this is the very tip of a neuron. Neurons have big cell bodies, and they have these fibers that go out to connect with other things. And at the very tip, they use actin and myosin to sort of pull themselves along. But because they're very short, or they're very sharp, they can sense the electric field very well. So they know where the electric field is, so they'll grow towards that. So this is an example of what a neuron looks like. So this is a cell body there, and these are all these fibrils it's sending out. They're called processes. And without a field, they go in all directions. With a field alone, they'll align themselves with the electric field. So the neurons can sense electric fields in the environment. Now, how do neurons repair after damage? If you want to repair a spinal cord to do a head transplant, you need to understand how they regenerate after damage. So there are two different types. There's the peripheral nervous system, which I mentioned before. Those are the ones that connect your muscles and receive from your senses. And there's also the central nervous system, which cells connect to other cells. So these are two different neurons connecting to each other. This is a neuron here connecting to muscle tissue. And we'll see how they respond differently to damage. So you give them some damage here, which is denoted by that red triangle. And they fall apart. They retract into the cell bodies. And as they begin to grow again, the environment here encourages new growth and repair, while the environment in the central nervous system is very hostile to new growth. And not only that, it's very difficult for them to find their match because they're long and thin, they're trying to reconnect, and they sort of miss each other like ships in the night. Whereas the muscle is very large, so it's very easy for the connection to be reestablished. So the third part is how nanomaterials interact with biology. So we're going to put everything together. So we have the graphene nanoribbons here. These are aligned in vertical and horizontal directions, so you can see how the neurons grow on them. So then you put neuron stem cells on this array, and you can see primarily that the neurons like to grow either vertically or horizontally. So you can see the fibers are going along the nanoribbons. So neurons like to grow along nanoribbons because as they send out their processes, they're long and thin, and the nanoribbons are long and thin, so they provide a nice substrate for them to grow along, and they're electrically active. The nanoribbons are conductive, so as the neurons are growing along, they can feel the electric field, and they can sense the neurons from the other end. I'm trying to get to the next slide here. There we go. Oh, I went one too far, going back. So in this case, we put a graphene nanoribbon between the two cells as they're trying to grow. And not only does this provide sort of a little microenvironment that the cells can grow nicely in, so it sort of allows them to grow in the hostile environment, but it also provides an electrically active substrate. So now these neurons sort of can feel each other with electric signals across the gap. So now when they grow, they'll actually make a reconnection. So this is how you reconnect a spinal cord. You add the graphene nanoribbons so that the neurons can reconnect with each other. And if the neurons can reconnect, you can get the spinal cord to reconnect, so you can do a head transplant. Next slide. So now we understand how to do all these things, let's see them in action. So we have a hard problem, the head transplant or the spinal cord fusion, which would also be more broadly applicable to paraplegics and quadriplegics. We have a multidisciplinary approach. You know all that, how that all works now. So now we can go to our new idea. So this is a paper we published. So it's spinal cord fusion with graphene nanoribbons, or polyethylene glycolated. So that's the water-soluble things that I showed you on the sides of it, graphene nanoribbons. So how do we do the surgery? So this is the brain of a, oh, I pressed the wrong button. So this is the brain of the animal here, and there's a spinal cord coming back here. You can count your vertebrae, 1, 2, 3, 4, 5, and we do the transection after 5. So you open up the surgical window, and then you support it with a nice spinal cord hook, which is actually made in Canada. And then you take a very sharp knife and cut completely through between C5 and C6. So this is completely paralyzed animal. The animal is a quadriplegic. They can't move or walk at all. And then you put the graphene nanoribbons in the solution. So you take graphene nanoribbons, you put them at the gap, and then you close it back up, and then you let the animal heal. And we'll see what happens. So before functional recovery is observed, where the animal can get up and walk around, we'll see electrical reconnection happening first. So that's where you can stimulate at the toe of an animal and watch and record from the sensory cortex of the brain. And this is what a normal animal looks like when you provide varying currents my laser pointer is dying a little bit, that's okay. When you provide varying currents, you'll see a response in the brain. Whereas the control, where you have done the surgery, you've cut the spinal cord, but you haven't repaired it, there's no response at all, and that's what we expect. And if you repair them with graphene nanoribbons, you see that there is a response. And this is only 24 hours after the surgery. So there's an electrical connection already only 24 hours after the surgery, which is really important because the spinal cord, once it is disconnected from the head, it starts to fall apart, and it needs to know there's still a head attached so it can recover. And this is a graph of what the functional recovery looks like. I'm going to show you a video representing this in a second. So the locomotion is scored on a 21-point scale. A perfectly functioning rat scores 21 points, but a paralyzed rat scores 0 points. So on the day of the surgery, they can no longer walk at all, and then you see them recover over time. And with polyethylene glycol, which is the solution Sergio was using before I came on the scene, you end up stagnating at around 8 on the 21-point scale. And I'll show you what an 8 looks like, and it's not very encouraging. But with the graphene nanoribbons, you get to about 19 out of 20 or 18 out of 21, which is almost perfect motor control. So now we'll watch the video. So this is an animal that had their spinal cord completely severed. So they were quadriplegic, and now you're going to see it 1 week afterwards, then 2 weeks, and then 3 weeks. So here we see the animal after 1 week. So you can see it's moving around. So this is scoring an 8 out of 21. So this is the best that there was before the graphene nanoribbons came on the scene. So you can see moving around, his movement isn't very coordinated. It's potentially because the neurons that used to control the leg maybe now control the arm, so there's some sort of recalibration that needs to happen in the motor cortex. Now this is 2 weeks afterwards. So you can see he's walking around much more readily. He's a very happy rat. You can see his front paw is a little bit curled right there. So he doesn't have fine motor control yet, but he has at least the gross motor control. He can walk and move the hands. And now this is 3 weeks after surgery. He's really going for it. These are the little food pellets there. He's really happy. This is how he picked animals up by their tail. This is normal. It doesn't hurt the animal. They're very light. So then you put it back in his cage. He wants to go back in there. Oh, he wants to escape. And again, we'll see him walking around. So the video will play for a little bit longer. So there he is walking around, and not in this clip, but in the next clip, you'll see him touching the animal to demonstrate response to the formerly paralyzed region. So you can see him sniffing around. So he's not walking at a 21 point, so he's still not perfect, but it's very close to where we would need to be. So this would allow the head transplant to occur, and would also allow potentially people who are quadriplegics or paraplegics to walk again. With that kind of spinal cord damage, there's a bit of a rough cut, so you need to make 2 new cuts and bring those cuts together. Yeah, but there he is. And so you can see him responding to touch there. And normally animals like that would not be able to respond to touch in that region. And this is the multidisciplinary team that made it happen. So this is my prof, Dr. Tour here. This is Sergio Canavero, and this is the person who did the animal research there. Thank you.
So William, you've met the surgeon.
By Skype, yes.
Yeah? And when were you last in touch with him?
I was last in touch with him, I think, about 2 months ago. We continue on Skype conversation.
Will you be present when the actual operation takes place?
I don't think so. I'm the chemist. I'll provide the materials, or at least the knowledge to make the materials. Yeah. But I'm not sure. I don't think I'll be there.
You don't like the sight of blood?
I like to stay on the chemistry side of things. It's a little bit easier.
And he's gone strangely silent,
he has.
Even though it's scheduled for just a few months from now. Is it because he's finding it hard to find a place to do this and a sponsor to do this?
He's told me he's got something big coming, but he's keeping it close to his chest, so I don't know what's happening.
Mm-hmm. Okay. I don't know what to say after a while.
We'll find out, I guess, sometime soon.
But, you know, if ever you get tired of your face one day, not so much.
Okay.